Hello, class. Today, I'd like to just talk about the structural features that influence pKa. So as we talked about previously in class, Ka is a equilibrium constant in this case for an acid, and it's given by the concentration of products over the concentration of reactants. So for this general acid-base equation, that would be the concentration of the hydronium ion multiplied by the concentration of the conjugate base over concentration of the conjugate acid. And as you'll remember, we don't include water in this equation because it is our solvent and its concentration doesn't change over time. So when we think about Ka as an equilibrium constant, it defines equilibrium. So if we have far greater products, then we expect to see a Ka that is greater than 1. And if we have more reactants, we expect to see a Ka that is less than 1. And the other definition that we need to talk about is pKa, which is a convenient way for to represent the Ka, and it's given as the negative log of Ka. And so in this case, for when the Ka is greater than 1, we'll have a pKa that is less than 0. And then where the Ka is less than 1, we expect to see a pKa greater than 0. And so when we look at this equation for a strong acid such as hydrochloric acid, we know the Ka is given as the concentration of that hydronium ion multiplied by chloride ion over each concentration of the acid HCl. And that's given as 10 to the 7th. And this really defines that this highly favors products. And that favoring of products is due to the stability of the products. And so all of that is to say that this chlorine ion must be very stable if we have a strong favoring of products rather than seeing back reaction to our reactants. And so with a Ka of 10 to the 7th, let's put a plus here, the pK is equal to the negative log of that 10 to the 7th. And so the pK is equal to -7. And so this makes sense for that definition of pK less than 0 indicates, Ka greater than 1, and therefore, in this case, a strong acid. And so, like I mentioned, the stability of the conjugate base, in this case, the chloride ion, is key to the strength of the acid, where the more stable the products, and therefore the higher the Ka favoring the products, that means that we see less back reaction. And so the two features I want to talk about today that influence Ka and relative Ka when comparing acids are electronegativity and atomic radii. And so the first of these is electronegativity, and I show here the electronegativity chart. And I'll remind you that the definition of electronegativity is the power of an atom to attract electrons to itself. And so when we use electronegativity to talk about the structural features affecting pKa and relative pKas, we think about that when looking across a rower period of the periodic table. And so I show here 4 compounds from the same row: methane, ammonia, water, and hydrofluoric acid. And I'll give below their pKas. And so we can see that as we move from carbon to fluorine, that pKa is going down. So as we move this way, pKa goes down. And I give, once again, that definition of pKa and Ka below. I've flashed up the electronegativity chart here. And if we write down the electronegativity for our heteroatoms, so fluorine, oxygen, nitrogen, and carbon, we can see that those electronegativities are 4.0 for fluorine, which is the most electronegative atom. Oxygen is 3.5. For nitrogen, it's 3.0. And then for carbon, that's 2.5. So we can see here that as the electronegativity increases, we're seeing that lowering of pKa, which suggests that a higher electronegativity corresponds to a lower pKa. And so a way to help explain this is we can think about the difference in electronegativity between hydrogen and the atom it's attached to. So we'll calculate that difference in electronegativity using the electronegativity of hydrogen, which is 2.1. So for carbon, we have 2.5 for carbon minus that of hydrogen, 2.1. So we have a difference of 0.4. For nitrogen, hydrogen bond, that's 0.9. For the OH bond, 1.4. And for the hydrogen fluorine bond, 1.9. And so we talked about differences in electronegativity early in the course when talking about polarity and dipoles, where we talked about types of bonds, such as the covalent bond with an electronegativity less than 0.5, and a polar bond that has an electronegativity between 0.5 to 2.0. And so you'll remember that covalent bonds have equal sharing of electrons, while polar bonds have unequal sharing. And so we can see that the electronegativity for methane is 0.4. So that's a covalent bond. And then for our other three compounds, those are polar covalent bonds. And with this polarity, it means that with that unequal sharing, we imagine that there's more electron density around the more electronegative atom. So in this case, nitrogen has some amount of partial negative charge or electron density surrounding it. And then as we increase in the difference in electronegativity, we can imagine that that partial negative charge gets bigger, or it's more localized to that heteroatom. And so when we think about those partial charges and then look at the conjugate bases after there's deprotonation, all of these all of the compounds will have a formal charge on that heteroatom. And looking at when we think about the former partial charges, where we had some partial charge on nitrogen, a little bit more on oxygen, and a little bit more on fluorine, that's not too dissimilar from their current state. So we can imagine for fluorine that had this large partial negative charge, that's not too dissimilar from its now formal charge. So its high electronegativity and its power to withdraw electrons to itself suggests that it has stability with that negative charge. And that stability of that conjugate base is the reason why we see that increase in pKa. So that high electronegativity and high dipole helps us to understand the high stability of fluorine and that increase in pKa. The second thing I wanted to talk about was the atomic radii, because even though fluorine is that most electronegative atom, its pKa, as we saw earlier, was 3, while for hydrochloric acid with a electronegativity of 3.0, that has a pKa of -7. So their electronegativity is not the only important effect at play here. So the second effect I'd like to talk about are atomic radii or atomic size. And I just show the chart of atomic radii that you had seen previously. And in this case, atomic size dictates pKa trends when looking down a column and tends to dominate overall. So here I show the halide series of hydrofluoric acid, hydrochloric, hydrobromic, and hydroiodic. And you can see that we're looking at a decrease in that pKa. So we're getting more and more acidic. And when I'm going to flash up the size of those, the atomic radii for those, and you can see that we're seeing an increase in atomic radii as we go down this column here. And so I'm going to represent that pictorially for the conjugate base. And you see here an increase in the size of these atomic radii. And you can imagine for fluorine in its valence shell that the electrons are very close to each other. So there's some repulsion and some destabilization of that state. But for something like iodine, the electrons have a larger area to explore in that valence shell. And that helps to bestow stability because there's less repulsion and the electrons are in a more stable state. So all of this is to say that the larger the size of the anion, there's more room for the charges to disperse and delocalize. And we see with that delocalization of charge, a decrease in the pKa and things becoming more and more acidic.